Hi everyone. In this video, we're going to cover section 2.4 on something called continuity. Continuity comes from the word continuous, and I will formally define it on the next slide. But for now, we're going to take a look at these 1, 2, 3 graphs to kind of understand the requirements of continuity. And if I'm looking at a graph, continuity is simply, can I draw the curve, the whole thing, over its whole domain without picking up my pencil, right? I couldn't there. Can I draw this curve without picking up my pencil? Technically, no, because there's a hole. And then can I draw this curve without picking up my pencil? No, because I got to go up there and then back down here. Visually speaking, continuity is a simple concept. Can I draw it without picking up my pencil? But in practice, in working with functions in calculus, we need a formal way to define it in terms of f being defined at a point and in terms of limits. All right, so for each of these three graphs, we'll start down here with this one. This function is not continuous, right? Because, well, it like jumps, right? So what formal reason could I say other than it jumps, right? We have f of a, whoops, that was, let me grab a different color here. F of a exists at that point right there. But if we think back to how we talk about limits, right? The limit as we approach from the left and the limit as we approach from the right are different values, and therefore the limit doesn't exist at that point. Okay, the limit doesn't exist, and that's the more formal reason for why our function isn't continuous. Visually, it's a piece of cake. I can't draw it without picking up my pencil. Okay, but we need that formal reason for when we don't have graphs, when we're just working with function notation. With this guy up here, this one, why is that one not a function? Well, where are we at a, right? At exactly, the limit exists, the limit is defined, right? That's the limit we're approaching some y coordinate, that exists. But what about f of a? F of a, it's nowhere on the graph, right? It's non-existent, it doesn't exist. So the function has to exist at the point for it to be continuous. So you have to be able to pass through the point, again, without picking up your pencil. And then this one over on the lower right here, right? In this case, the limit exists, right? The limit as I approach a from the left, the limit as I approach a from the right, they're both the same value. But is that the same number? Well, they're not numbers here, but is that the same value as f of a? And the answer is no. Okay, so my limit and my function value have to be the same in order for my graph to be continuous. Okay, so that's the visual representation of what we need to have for a function to be continuous at a point. Now let's look at the formal stated definition. All right, here we go. For a function to be continuous at a point, a function is continuous at a point if and only if the following three conditions are satisfied. F of a has to exist. It has to be defined. The limit at a has to exist. And that limit and that function value have to be the same number. And if you go back in the video to where those three graphs, each of them fails one of these three conditions. So each of them would be considered discontinuous at the point A, because they are not continuous. Discontinuous, continuous, they're opposites of each other. All right. And so problem solving strategy, first we check to see if f of a is defined. If it's not, we're done. Then we compute the limit. We may have to look at the left-handed limit and the right-handed limit separately. If the limit doesn't exist, we're done. It's not continuous. If the limit does exist, then we go on to check 3 and see if they're the same value. If you want to read those more clearly, pause the video and read through them. But now we're going to use that to answer those 3 steps to answer this question down here. So we have a function, f of x equals x squared minus 4 divided by x minus 2. And is it continuous at x equals 2? Justify the conclusion. All right, so what are we going to do first? Let's start with step 1. What is f of 2? And the reason I'm checking 2 is because that's the point that the question asked me about. So if I substitute 2 into my function, x squared, oops, no, not x squared. Let me erase that. 2 squared minus 4 divided by 2 minus 2 equals 0 over 0, and that does not exist, right? Doesn't exist. Therefore, we can 3 dots, that's a cool mathy abbreviation for the word therefore. If you didn't know that, now you do. therefore, f of x is not continuous at x equals 2. All right, so that's as much work as you would need to do for that problem. Okay, but I'm going to do extra work because that's how I roll. I want to also compute the limit as x approaches 2 of my function. Again, I just want to do a little bit of extra work, beat this problem to death, see what happens if we were to move on to step 2. So my function, this would equal the limit as x approaches 2 of x squared minus 4 over x minus 2, which is the limit as x approaches 2 of x plus 2 times x minus 2 over x minus 2. And look at that, just like the last section, I have some canceling factors, and that remaining factor I can evaluate at 2. 2 plus 2 is 4. So step 2, the limit does in fact exist, but because of the first step, the function doesn't exist at that point. It can't possibly be continuous. Okay, but if we'd gotten an answer to the first part, well, let me label this as 1 now, and we had gotten an answer to the second part, then step 3 would be, are they the same number? And the answer would be no. Now let's look at another example addressing continuity at a point. And in this one, we have our piecewise function that kind of breaks into two pieces at x equals 3 for when x is greater than or less than 3. Okay, and that's the point that we're testing. All right, so step 1 from the previous slide is we're going to check and see what is f of 3. And again, because the question asked me about x equals 3. So for f of 3, we're substituting into the top branch of our function. F of 3 is equal to negative 3 squared plus 4. Now that's not parentheses negative 3 squared equals positive 9. Don't make that mistake. The exponent happens first, 3 squared is 9, and then there's a negative sign in front of it. So that's negative 9 plus 4 is negative 5. All right, so there's our function. It exists. Cool. Let's move on to the second step. What is the limit? The limit as x approaches 3 of our function? Well, in order to answer that question, because we have a piecewise function, we've got to say, oh, I got to check the limit as I approach 3 from the left of f of x, and then the limit as I approach 3 from the right of f of x. Look at that. I just used my fancy copy and paste feature. So if I want to start with approaching from the left, so this guy here, so we'll label this as 2a and 2b. I want the limit as I approach 3 from the left. Well, if I'm approaching from the left, that's if x is less than or equal to 3. So I'm using this top branch of our function, and that is negative 3 squared plus 4. Now, I didn't write the parentheses in this one, but the answer is going to be the same, negative 5. All right, and if I approach 3 from the right, limit as x approaches 3 from the right, we're substituting into the bottom branch of our piecewise function. So that is 4 times 3 minus 8. This is equal to, let me write it this way. There we go. 4 times 3 is 12. 12 minus 8 is 4. So my limit as I approach from the left is negative 5. As I approach from the right, positive 4. Hey, look at that. Those are two different numbers. Therefore, the two-sided limit does not exist. Okay? Two-sided limit does not exist. So what does that mean? All of that work means that we are not continuous at 3. So let's say, therefore, f of x is not continuous at 3. It fails number 2 of our checklist. The previous one, it fails number 1 of our checklist. If you want to see an example that fails number 3 of the checklist, then there is one more example involving condition 3 in OpenStax. So check out the text, and that'll just give you one more example. All right, now we encounter a theorem involving continuity of polynomial and rational functions. And this one kind of can save us some time if we know what this theorem means. Basically, polynomials, rational functions, they're always continuous at every point in their domains. So piecewise functions, that throws wrenches and things. But if I just give you some old generic polynomial function like f of x equals 3x cubed minus x squared plus x plus 1. That's a polynomial function that is continuous on for all real numbers. Continuous, or not, Emily, right, is continuous for all real numbers. Okay, and the rationale behind that, there's a kind of formally stated proof on OpenStax. Excuse me, but the rationale behind that is if I were taking the limit at some point, that would involve evaluating the polynomial at that point. So the limit and the f of that value are always going to be the same thing based on how limits work. All right. So that one, hopefully, fairly straightforward idea. All right, and here's an example where we use that theorem. So for what values of x is that function, that rational function, continuous? Well, according to the theorem, it's continuous for all x in its domain. So what can't be in the domain of that function? Right. So we say x cannot. Whoops, I didn't mean to zoom in there. X cannot equal 5. Right. That's what fails. That's the one point of discontinuity for that whole function based on the theorem above. X cannot equal 5. So for what values is f of x continuous? We can write it using interval notation. It is continuous over the interval, continuous on the interval negative infinity. Whoops, I forgot my negative sign. There's a negative sign. Negative infinity up to 5, and then a union 5 comma infinity. So those are the two pieces of that function, and it's continuous over those pieces in their entirety, from 5 up to positive infinity, from 5 down to negative infinity, and then we just have that excuse me, that one single hole at x equals 5. So looking more closely now at discontinuities, points of discontinuity, we give them some fancy names. The first one is a removable discontinuity. This a here is a removable discontinuity. So f has one of them. If the limit at a exists meaning that it is some real number L, right? If the limit exists but it's still continuous, then that is a removable discontinuity. All right, a jump discontinuity, f has a jump discontinuity if the limit from the left and the right both exist, but they're not necessarily the same value. Okay, and again, exist means that we get some real valued number, not infinity or negative infinity. So this is called a jump discontinuity for maybe obvious reasons. And then an infinite discontinuity at a if the limits as you approach that value are positive or negative infinity. This next example refers to one that we actually did previously, that this function is discontinuous at x equals 2. Then it says classify the discontinuity as removable, jump, or infinite. So we've previously seen earlier in the video that f of 2 does not exist. The limit as x approaches 2 of f of x was equal to 4. So we didn't need to break this apart into the limit from the left and the limit from the right, but we got 4 for our limit. All right, and because the limit exists, but we have a point of discontinuity, this is called a removable discontinuity. Removable discontinuity. All right, and then the other problem here we also did earlier in the video. And earlier on in the video, we got f of 3 is negative 5. The limit as we approach 3 of our function is also negative 5. Oh, 3 from the left, excuse me. And then the limit as x approaches 3 from the right of f of x was, what did we get? 4 times 3 is 12, minus 8 is 4. Okay, so the two-sided limit does not exist. We got two different answers for that. Actually, I don't need to write all that out. Because we got different answers from the left and from the right. That tells me that this is a jump discontinuity. A jump discontinuity. Whew. T-I-N-U. Sorry for the messy handwriting. Jump discontinuity. We can talk specifically with functions about what intervals they are continuous over, and we define continuous from the left and from the right by seeing from which direction does the limit equal the function value. Does the limit from the right equal the function value, or does the limit from the left equal the function value? And so, like, visually, what we're talking about, if I have my grid here, if I'm coming to a point from the left and filling in my circle at A, that would be an example of continuous from the left, and then I would have to have an open circle and going to the right, right? That's a visual example of what continuous from the left looks like. And then continuous from the right, if I have, let me do a similar picture here. This is going to have to be an open circle filled in there. That would be a visual example of continuous from the right. See, the limit from the right is equal to the function value at that point. And here the limit from the left is equal to the function value at that point. You can go back to the previous example, skip back, I don't know, maybe a minute and a half into in the video, and see which direction that function was continuous from. The piecewise one. Was that one continuous from the left or from the right? All right, let's scroll down a little bit here. This next example wants us to state the intervals over which the function is continuous, and the way that we do that is to find the points of discontinuity. So what can't be in the domain of our function? I'm going to rewrite my function f of x minus 1 over, I'm going to factor it though, so I can find the zeros in the denominator. That would be the values that are undefined. X times x plus 2. All right, so we find that x cannot equal 0 because of the first factor, and x cannot equal negative 2. Those are the only values that x cannot be, so our function is continuous over the following intervals: negative infinity up to negative 2. Throw a little u there for union. You're joining them together. Negative 2 up to 0. Notice I'm using parentheses for all these numbers. X can't be those numbers, so they should not be square brackets. And then one more union, 0 to infinity. So those are the intervals over which my function is continuous. Now we end the section talking about what is called the intermediate value theorem. The intermediate value theorem is something pretty useful in maths, and what it says, and if you want to pause the video and read it first, you can, or I'll just kind of talk about it. What it says is that if I have a function that is continuous, that's a really important part. It's continuous over some interval from a to b, and if I pick any number, if z is any real number between f of a and f of b, okay, so z is up here on the y-axis between f of a and f of b. What the intermediate value theorem says, that there must be some number c here. There must be some number c inside of the interval from a to b such that f of c equals z. Right? If my function is continuous, then I can pick a number over there and be guaranteed to find something that maps onto it. If it's continuous, I can be guaranteed to find something that's going to map onto every number between f of a and f of b, right? So that I could pick some other number, some number over here, and I can be guaranteed. And obviously we can see this with the graph, but the point in the theorem is that I don't need the graph. If I know it's continuous, I can be guaranteed that I can pick a y coordinate over there and find something between a and b that maps onto that y coordinate, and we'll do that with this example. And it really requires that the function be continuous. If it's not continuous, then it could jump all over the place. But because it is continuous, we're guaranteed to find that value. Okay, so here for this example, we're given a function, and we have to show that it has a zero over the interval from 0 to 1. And the way that we're going to do that is we're going to first find f of 0 and then find f of 1. And I'll explain to you how that helps us. So if I substitute 0 into my function, 0 cubed minus 0 squared minus 3 times 0, add 1. I think I can handle that math. It's 1. And if I substitute 1 into my function, 1 cubed minus 1 squared minus 3 times 1 plus 1. This one I've got to make sure I get correct. 1 cubed is 1 minus 1 squared. 1 minus 1 is 0. Negative 3 times 1, negative 3 add 1 is negative 2. Negative 2. All right, so let me write this more compactly. F of 0 is equal to 1, and f of 1 is equal to negative 2. So if I sketch this out onto a little tiny set of axes here, okay, and let's put 1 over there, make it nice and big, negative 2 down there. All right, so f of 0 is 1, like that. F of 1 is negative 2. Okay, show that the function has a 0 over the domain. It is continuous because it's a polynomial function. I probably should have said that earlier in this problem. Let me throw it up here with a star. Continuous because f of x is a polynomial. So if it's continuous everywhere, but specifically over the interval from 0 to 1, what's it going to have to pass through? It's going to have to pass through the x-axis somewhere in there. I don't necessarily know where, but somewhere in there it has to pass through the x-axis. And that's basically what the intermediate value theorem says. It's guaranteed to hit 0. There's some number that maps onto 0, in this case between 0 and 1. And this cubic equation is solvable. It might be a little bit challenging to solve. Maybe I can factor it. Okay, but some number between 0 and 1 does in fact map onto 0. Like we're guaranteed because it's continuous. All right, that is the last topic in this section. Really the key is that you understand those three important points for a function to be continuous. All right, we get started on the homework. Please let me know if you have questions on this stuff. Thank you very much for listening and have a wonderful day.